Hello, everyone. This is episode 3 of Open Hardware TV. And as we've done with previous episodes, we pre-record the content to try to increase the quality of the video for everyone. And all of our speakers are joining us here today. You can see them all. Wave hello, everybody. And we'll be live viewing the episode together with all of you attendees today. There's about 37 minutes of content. Then we'll come back for the live Q&A at the end. So in just a moment, we'll switch over. If all of our speakers can turn off their video, we'll switch over to the live stream and we'll see you back at the end of it for the live Q&A. In the meantime, enter your questions in the Q&A chat box so that we can have those queued up. We'll read them out at the end and get all the speakers and panelists to answer the questions. So with that, here comes the live stream content. All right, so let's jump right into it and take a look at the agenda for today's episode. So for episode 3, the focus is going to be on our hardware and software task groups and the projects that we have underway within the task groups. But first, I'll give a quick overview of the organization. Then I'll bring the leadership team in from the task groups. And then we'll dive into some of the projects that are underway within our hardware and software task groups. So the Open Hardware Group is a global nonprofit organization focused on open source collaboration around hardware and software designs. And we collaborate on open source cores, related IP, infrastructure, tools, and software. And the initial focus is a family of Core-5 open source RISC-V cores that originated at the University of ETH Zurich under the leadership of Professor Luca Benini. We'll talk more about that in a second. But we've got an international footprint, developers all across the world in North America, Europe, and Asia. And really what we're providing is an open source infrastructure for hosting industry quality open source IP for use in high volume production SoCs. So we leverage commercial tool flows and curate those artifacts in such a fashion that they fit easily, stitch easily, if you will, into the design flows of major semiconductor companies. We have strong support from industry and academia, and as you can see here on the following slides, many participants on the industry side, as well as on the academic and research side, and then as well a strong roster of partners that are helping us deliver these open source artifacts. So we're very happy and fortunate to have everyone participating, and we continue to grow at quite a rate. So as I mentioned, the initial projects within the Open Hardware Group are 2 cores based around the Core-5 family of open source RISC-V cores. And these cores originated, as I said earlier, in the Pulp Platform Research Group at ETH Zurich under Luca Benini's leadership. They're very popular cores that have been adopted in industry. And what we're working on is producing high quality verification test benches, updating the cores from a feature functionality standpoint, and verifying those cores for use in high volume production SoCs. So in particular, the RISC-V core, which we now call the CVE4, a 32-bit 4-stage embedded class core, is one of the projects that we have underway. And then Ariane, now called the CVA6, with both a 32-bit option and 64-bit option, 6-stage application class core capable of running Linux. If you missed the earlier episodes of Open Hardware TV, you can learn more about the verification infrastructure that we have in place by looking at the playback on-demand video of episode 1, which aired on June 18th. And then on July 16th, we aired a cores overview and deep dive, if you will, for the Ariane core and RISC-V core, CVA6 and CVE4. But for today, we're going to focus specifically on the hardware and software task groups that are building support infrastructure around these cores. And right now, we'll bring in our leadership team for the hardware and software task groups. Hugh Pollitt-Smith from CMC, who chairs the hardware task group, Jeremy Bennett from Embecosm, who chairs the software task group, Yunhai Shang from Alibaba, who is vice chair of the software task group, and our own Florian Zaruba who is part of the Open Hardware Group engineering staff, is our Director of Engineering for the Hardware and Software Task Groups. And many of you may know him for his work on Ariane as he's pursuing his PhD at ETH Zurich. So welcome to the episode, gentlemen.
Hi, Rick. Good to be here.
Hi, Rick.
Great. So let's start off with the software task group. And as our chair of the task group, Jeremy, would you be able to walk us through the slides outlining the software task group?
Thank you very much, Rick. Yes. So the objective with the software task group is summed up in our two goals. The first is this will only work if we have a viable commercial ecosystem for software to actually encourage companies to actually create software that is suitable for Core5. And we don't just mean open source, we mean proprietary and open source. Okay. Now, there's a supplementary goal for those tools that are open source. We don't want to keep them to ourselves. We want them to be their part of the official distributions. So the question is then, what is the software that we cover? On the next slide, just give you a breadth of what this is. We've got compilers, the whole tool chains, the assembler, the disassembler, the linker, GCC, LLVM, and the libraries that go with them. And then the operating systems they support, from the smallest embedded operating system up to full-fat Linux, FreeBSD, NetBSD, and so forth. A lot of our work is done pre-silicon. So users need to not only be able to run on actual platforms and FPGAs, they need models. So we need models of the processor and indeed of complete systems. And they could be open source, they could be proprietary. We've got examples of both, Imperius with OVP Sim and tools like Verilator and QEMU. And thirdly, software developers who are using software tools need development environments. So we're going to need to have integrated development environments that understand Core5 and in particular, how to connect through debuggers to actual systems, whether models, simulations, or physical hardware. So Eclipse, Platform IO, and so forth. And at the heart of it, we'll hear later, we're going to have reference platforms. So all that software had better work properly on our reference platforms that Hugh will be talking about later. Lastly, where are we on this? Well, the good thing is Core5 is a RISC-V. So you can just take standard RISC-V tools and operating systems and IDEs, and they should just work fine. But we want to take advantage of Core5. So some Thales and at the moment, but we'd welcome anyone who else would like to join in, are working on improving the tools, particularly the GNU tools, working on the CV32E40P platform and Thales working on the CVA60. And the priority is to get those tools robustly tested. They've got to be good if you're going to use them for commercial code. You've got to know they work well. And my colleague Craig Blackmore will be talking about that later. And we're working on a pulp-specific IDE with debug integration. We've got two flavors, the Ashling RiscFree product, which Royston will talk about later, and there's also a free Eclipse embedded-based version, which Royston will also talk about. And in terms of simulators, well, we've got the open source simulators, and of course there's Core5 support available in Imperius OVP Sim. So thank you, Rick. I'll hand back to you.
Great. Thanks very much, Jeremy. We'll come back for a couple of questions about this in a moment, but first let's switch over to Hugh to talk about the hardware task group.
Thanks, Rick. Yes, the chief goal of the hardware task group is to support hardware implementations of the Open Hardware Group cores by defining, developing, and supporting SoCs, FPGAs, and evaluation development platforms, leveraging both proprietary and open source tools, and this for the cores and IP developed within the group. In terms of the responsibilities of the hardware task group, our efforts are focused on FPGA development kits, supporting architecture exploration, developing custom hardware accelerators for the cores, performing hardware emulation or hardware software verification and debug, develop applications and demonstrations, and develop training materials around these cores. Secondly, responsibilities around developing SoCs that are built in current node geometries, such as GlobalFoundries 22 nanometer, using cores and IP developed within the Open Hardware group, and then building development kits based on those SoCs for software and application development, demonstration, and training. In terms of the status of the hardware task group, I'll talk a little bit later about our first FPGA development ecosystem. And we're looking for collaborators to develop and enhance the current environment and future environments that can include enhancing the system architectures, such as different types of interconnect or adding peripherals and accelerators to the system, integrating additional tools and IP and development flows, demonstrating different JTAG probes, IDEs, operating systems on the target platforms, and developing application and demonstrations and training materials for users. And as I mentioned, I'll be talking about this environment a little bit later.
Great. Thanks very much. I appreciate the update from both of you guys, Jeremy and Hugh. So maybe let's just a couple of questions here. So we've also got Yunhai, who's a vice chair of the software task group from Alibaba on the panel here. Yunhai, can you maybe describe why this is important to you, and why is Alibaba engaged in this work with the Open Hardware Group?
Okay, thank you, Rick. As we know, Alibaba released the world's highest performance RISC-V processor, Xuantian 910 last year. This is a great step for RISC-V architecture. I'm very likely to participate in development of this processor, responsible for the software system. This experience makes me feel that RISC-V is a big opportunity for the chip industry and the software. But there are also many deficiencies, includes IC design and the software ecosystem and so on. I might be asked why I came to the Open Hardware Group. I think there are two challenges for the RISC-V architecture at present. One is production, and the second is software ecosystem. Open Hardware Group members are a group of developments with rich experience in product development. So I believe it will turn RISC-V into a product that everyone can get access and apply to anywhere. I will try to my best to build a good software ecosystem with Jeremy, including debugging system, IDE, graphic profiling, and so on. More fortunately, I have met a lot of friends in the group, including Jeremy, who is very professional and nice, Rick, full of leadership, and Mike, who is helpful and careful, and other very talented friends. It's a very interesting and exciting journey. Looking forward to you joining and working together with us. Thank you. Thank you, Rick.
Well, I'll send you a bouquet of flowers and a box of chocolates later. Thank you for the kind words and for your continued participation. So Florian, and many of you might know Florian as one of our speakers on episode 2 and the father of Ariane at ETH. Florian's our director of engineering for the hardware and software task groups. And maybe, Florian, you could talk to us about your experience at ETH. Obviously, the ETH Zurich program with the PULP platform has developed many cores, 2 of which are the seed cores in Open Hardware Group. And in doing that work, clearly you spent a fair amount of resources investing in hardware-based platforms, both FPGA and SoC-based, as well as tool chain work. Can you describe maybe your experience and motivations for that?
Yeah, so the core alone, unfortunately, isn't enough to be really productive. So you need an SoC around it that can range from very simple to more advanced SoCs. And we have actually built many of them. But as the PULP system and the PULP group is more coming from a research environment, we don't necessarily are interested in production-ready SoCs. We just want to demonstrate a particular thing, and that works in most of the cases, but it lacks standardization of interfaces somewhere. And so this is where the hardware task group and the software task group comes into play. So in the hardware task group, we want to switch over to standardized interfaces, well-standardized interfaces. We want to have systems which are well documented, which are easy to use, and which can be used by member companies and actually all companies, because it's developed in open source, to be a starting point for their own SoC implementations. And as mentioned, as a demonstrator platforms. On the software side, as Jeremy made perfectly clear, the compiler, coming from a research perspective, it lacks tests, it lacks maturity, and actually upcoming Craig will give you a very short demo on that. And so we hope that we can guide and direct this hardware tool, the software tool chain, to a more mature and production-ready. Great.
Thank you. Maybe just a couple more minutes before we get into the rest of the content. Jeremy and Hugh, can you guys speak to the motivations for your organizations, or why you have been wanting to participate, why you are participating in the Open Hardware Group ecosystem, and in particular, why you chose to lead these task groups? So Jeremy, why don't you start first? Give us a 60-second view on that.
Thank you, Rick. The key motivation for me is that I see software as being the poor relation at the moment in the RISC-V community. The whole Core-V Open Hardware Group initiative put software at the top level of the organization, recognizing that a processor is no good without software. I'm delighted to be part of that, and also to have buy-in to that key mission that software only works if you have a commercial ecosystem built around it.
Right.
Thank you, Rick.
Hugh, what's your take for CMC's participation?
Sure. I mean, as a not-for-profit supporting microsystems research in Canada, I guess our motivation is to bring our research community into this ecosystem so that they can do their research on sort of industrial strength IP and development flows and platforms. So that's sort of our motivation for participating.
All right, very good. Thanks, guys. Make sure you hang around because we have the Q&A session at the end of today's episode, and we'll bring you back in for those questions and answers. So now I'd like to change gears a bit, and we'll bring in Craig Blackmore from Embecosm to give us an overview of the software tool chain within the software task group. Craig, welcome to the episode.
Okay, thanks, Rick. Thanks for having me here. Hello, everyone. I'm going to talk about developing the GNU tool chain for Core-V. Firstly, I'll show an overview of the GNU tool chain. There are many tools, but we're going to start focusing on GCC, the compiler, GAS, the assembler, and the linker, which is part of binutils. There are more tools to address, but we can't address them all on day one. So what do we need for Core-V? There is currently a generic RISC-V toolchain upstream. And by upstream, I mean the official distribution of the GNU tools. So official GCC, official binutils. And you can download those, compile them, and they will work on Core-V, but you won't get support for the Core-V specific extensions. So that's what needs to be added, the Core-V extension support, starting with assembler linker support so we can assemble those instructions and use them. Built-in intrinsic functions so we can explicitly use these instructions in C++ code. But the ideal is that GCC will generate these instructions for you automatically. And that's the larger part of the task. So we'll start with basic support that will allow you to assemble these instructions and use them explicitly, and then move on to optimizing automatically in GCC. And the goal is to contribute all of the support upstream in order to ensure it can be maintained long term. Who's working on this? There's myself and 3 others from Embecosm on the left. We're working on 32-bit. And on the right, we have Zbigniew Chomsky, who's from Thales and also with the University of Bristol. He will be working on 64-bit, and we expect to work together because there will be synergies between the two. I'll focus mostly on CV32 in this talk. And so our plan for this work is to take what we have available at the moment, which is the pulp toolchain. And this has been developed by ETH Zurich and the University of Bologna. And this is a research toolchain driven by academic research. It was branched off from mainstream tools, upstream tools 3 years ago. And there are various contributions there that need to be updated to the latest GCC. So 3 years later now, things have moved on. Bring things up to date with the latest, and then try to contribute this back to upstream. And our plan of attack is to start with the pulp research bin utils. At the moment, there aren't any tests for the new Core-V features in bin utils. So we intend to add these tests and make sure they're passing to ensure a degree of commercial robustness. Once we have a bin utils, a stable bin utils with Core-V support, we'll then move on to GCC support. The plan here is to jump straight to the latest GCC. And one of the reasons for this is because GCC has changed so much in the last 3 years. We don't want to do all the work on 3 years ago GCC and then have to reinvest all that effort again. So we're going to go straight to GCC 10, and many new tests will need to be added to GCC as well to test these new features. Once we have a stable GCC with basic support, again, this is not the full automatic generation GCC yet. Once we have that, we'll then migrate bin utils GDB to the latest as well. That's the initial work to get the basic support, and then we move on to future work. So optimizing GCC to automatically generate Core-V instructions, providing automatic optimization in GCC for things like loops, generating hardware loop instructions for them, and generating post-increment addressing instructions. So these are Core-V specific features that are not seen yet in standard RISC-V. It may be that other people see a value in them, and then they will become the RISC-V standard. And an advantage of getting this upstream is there is more visibility of these features as well. Our plan is to create a new vendor, Core-V. So we'll be the vendor, Core-V will be the vendor. And rather than seeing RISC-V 32 unknown alpha, you'll now see RISC-V Core-V unknown alpha, and you'll know that you're working with a Core-V toolchain. There's also scope to hand code versions of the standard libraries so that they're optimized specifically for Core-V. And an advantage of the open hardware group is we have both hardware and software toolchain expertise, and we intend to make it easy to add new generic instruction set extensions to Core-V. So with that collaboration there, we can make it easy for people to add these instructions as they wish. We also provide downloads of the tools on our website. We have pre-compiled binaries for various operating systems. And we also provide the links to the source code and the build script that produced those compilations, produced those binaries, and the test results to go with them as well. I'd like to finish by showing a quick demonstration of assembler testing, and I will switch to my terminal now to show you that. So in this directory, I've got a build of the current pulp toolchain, the current pulp bin utils, and I'm just going to run the assembler tests. So check gas being the GNU assembler. The tests for the assembler run very quickly, and we can see that most of the tests have passed. And this is actually in line with GCC, with bin utils at the point where pulp branched off. But there are two issues here. At the time pulp branched off, there weren't any RISC-V specific tests, so none of the standard RISC-V tests are being tested. none of the standard RISC-V instructions are being tested, and none of the Core-V instructions are being tested either. So there's 2 tasks there to bring the test suite up to date. And that's where we start our journey. Thank you very much for listening. I'll be there in the panel if there are any questions at the end.
Great, thanks, Craig. Appreciate your contributions. Thank you for sharing that. All right, now we'll move on to some IDE work that's happening in the software task group. And we'll bring in Roshan O'Keefe and Rajesh Sajibabu from Ashling to give us an overview of the IDE environment and debug environment that we're working on. Welcome to the episode.
Thanks for the introduction, Rick. So Ashling is a member of the Open Hardware group, and we're working on IDE and debug tools for Core-V. So I'd like to give you a quick introduction to Ashling, then I'll run through the solutions available for Open Hardware Core-V development, and then we'll have a live demo of the tools from Rajesh. Ashling is specialized in development tools for embedded processors and MCUs, such as IDEs, compilers, debuggers, hardware debug and trace probes, for a range of embedded architectures. And we also provide engineering services for custom tools requirements. And we have specific expertise in complex real-time debug tools, including high-speed debug connection, high-capacity trace probes, code coverage, profiling, and so on. Ashling's RiscFree IDE is the commercial-grade software development environment. So it's an Eclipse-based IDE for RISC-V development. And it's a seamless environment for everything from writing and building your code to simulating and debugging your hardware. So it includes the Eclipse-based IDE, the debugger, for use with the Ashling Opel XD probe, and also for use with OpenOCD. It includes the RISC-V compiler tool chain with full build support, QEMU simulator, OS debug support, code coverage, and multi-core debug support for homogeneous and heterogeneous debugging. So here you can see the prototyping environment for the Open Hardware Core-V development. On the right-hand side, you can see the Digilent Genesys2 FPGA board, which is an advanced, high-performance, ready-to-use development platform based on a Kintex 7 Xilinx FPGA. On the left of that, you can see the Opel XD probe, and then the RiscFree IDE, which includes project wizards and ready-to-go Eclipse project for Core-V to run on the Genesys2 board with pre-configured build settings and pre-configured debug configuration setup so that you can easily connect to the board and download the code and so on. A second solution which we have is the Open Hardware IDE for Core-V. So this is very similar, except that it's a freely available open source development environment created by the Open Hardware group. It's also an Eclipse-based IDE for Core-V development. It includes the compiler toolchain for RISC-V provided by Embecosm, as just described by Craig. And it has OpenOCD support and also provides support for Ashling Opel LD probe with the ready-to-run examples for the Genesys2 board, getting started guide, and this is available from September. So now I'm going to hand over to Rajesh, who'll provide a demo of RiscFree with the Opel XD and the Genesys2 board, showing you how to build a Core-V example program and launch a debug session using the Opel XD connected with the Genesys2 board.
Yeah, thanks, Rosen, and hi all. I am Rajesh from Ashling, and today I'll be quickly demonstrating how to debug a Core-V MCU-based system using Ashling RiscFree IDE. RiscFree IDE is based on Eclipse, and this is for debugging applications, building and debugging applications for different cores like ARM, Synopsys, Arc, and obviously RISC-V cores. Today we'll be focusing on the RISC-V cores and the Core-V core. And Ashling is also working on another IDE, an open source IDE, the Core-V IDE, which will be contributed to the Open Hardware group, and that will be the IDE for debugging Core-V cores. So all the features which I'm demonstrating today and all the look and feel, they'll be same as what we see in the Core-V IDE. So look and feel, they're going to remain pretty much the same. So now we'll jump into demo. So in my system today, I have I have set up. I'll explain my hardware. I have a digital Genesys2 board in which I have a Core-5 MCU FPGA running, and this is connected via the JTAG pins to the Ashling OpenHW debug probe. So Ashling OpenHW debug probe is a JTAG-based debugger for JTAG debugging, and this is connected to my PC through the USB port. So coming back to the ID, RiscFree ID, we have a Core-5 sample project bundled, so it's ready to go. So I just right-click, build the project, and it's built. So now we can straight away start debugging. We'll jump into debugging the application. So that I'll just go to the debug configurations. So under the RiscFree debugging, I'm creating a new launch. So just double-clicking there, we have a new launch created, and you can see the project has been picked up, and the L file has been picked up from the active project. So we go to debugger tab. So that's where we choose the actual core. So we are choosing the Core-5 core here. So rest of them, they remain as it is. The probe has been picked, the debugger probe OpenHW. You can see it's being listed here. And then we have the JTAG connection selected. And the JTAG frequency, OpenHW probe supports up to 100 megahertz. So today I'll choose something optimum for the FPGA I'm playing with. So that is 15 megahertz. So I'm choosing 15 megahertz here. Remaining, we leave it as it is. We go to the startup tab. So there we are loading the image, obviously. We are loading the symbols. So I'm putting a breakpoint at main, and then we resume. So once I press apply and debug, what we expect, the program is now downloaded to the target, and the program, we execute the program, and it should stop at main. So now we can see the debug views are getting updated. So we can see the program, it has run to main, and the debug view updated, the Core-5 heart is halted. So we can see the call stack here. So I'll also quickly walk through the other debug views. So in register views, we can see the general purpose registers. Obviously, we have the custom CSR registers, or the CSR registers. And the CSR registers, we even have the bit description. So like it just makes things easy. Like it has something which we can read and understand, okay, what is the architecture? So we don't just get the raw data. There is no need to go back to our data sheet and understand what it means. The bit descriptions are here. So we understand this is okay, an RV32 system. And obviously we have the disassembly view, so we have the disassembly. And all the basic views like variable view, what are the current variable views, breakpoint view. So we can see I have already set a breakpoint here. So maybe I'll just run and see, so that breakpoint has been hit and the register values are updated. All the views are updated. And then we have the memory view. So this 1C0 range is our RAM area. So we can see the RAM, the data has been updated. So memory view, registers, disassembly, variables, breakpoint view. So maybe we'll do some runtime operations like step out. So we should step out from this function. We are here, maybe we'll do the step into, we'll be stepping into the function, and then maybe we'll run again. So we should see the breakpoint being hit and the registers are updated. So these are just the basic features I'm explaining today. I'm not going into more details. And once we have the Core-5 MCU ID, we'll be seeing pretty much the same. All these views, they remain the same. So from an end user perspective, it's not going to change. And yeah, so if you need more details, you can visit Ashling website and we can contact the support team. We'll have more details shared. Thanks, guys. Thank you.
Okay, great. Thank you to the Ashling team. Appreciate your efforts and your support in the ecosystem. Thanks very much. And for our last talk, we're going to switch over to Hugh Pollitt-Smith from CMC, who will give us an overview of the Genesys2 FPGA platform we're using for the Core-5 MCU. Welcome back to the episode, Hugh.
Okay, thanks, Rick. So I'm Hugh Pollitt-Smith from CMC Microsystems, and CMC is a not-for-profit based in Canada that supports microsystems research involving design, manufacturing, and testing of microsystems devices and systems. This includes research access to commercial suites of CAD tools for design and verification, multi-project wafer fabrication for diverse technologies, including GlobalFoundries 22FDX, Silicon Photonics, MEMS, And we also provide test and FPGA development hardware. While many of our offerings are focused on Canadian academics, we do offer products and services to startups in industry and non-Canadian academics. Within the Open Hardware Group, it's CMC's goal to develop, sell, and support development kits, FPGA and SoC-based kits, featuring open hardware IP, packaged with items such as JTAG debuggers, development tools, and pre-validated working configurations. As mentioned earlier, our goal is to develop these environments. The first of such environments is called the Core-5 MCU, which is based on the CV32E40P RISC-V core, formerly known as RiscFree, and developed at ETH Zurich and University of Bologna. Our first deliverable is an FPGA development environment that instantiates the core inside an SoC architecture with memory and peripherals. The environment is based around the Digilent Genesys2 Kintex 7 FPGA development kit, which features a Xilinx Kintex 7 FPGA with sufficient resources to support both the 32-bit and 64-bit Core-5 cores and platforms. It also includes 1 gigabytes of DDR3 onboard memory, a UART through micro USB, an FPGA mezzanine card connector for various expansion cards, HDMI and audio input and output, gigabit Ethernet, and PMOD connectors for low-cost expansion boards for various sensors, Bluetooth connectivity, etc., for IoT applications, as well as for connecting JTAG debug probes from a variety of vendors, including Ashling. The Core-5 MCU architecture is based on the Pulpissimo platform. Again, originally this was developed at ETH Zurich and University of Bologna for the RiscFree processor. Pulpissimo is a single-core platform that includes a tightly coupled data memory interconnect, RISC-V compliant debug module, autonomous input-output system called microDMA, which is connected to a variety of system peripherals such as UART, SPI, and I2C. So currently we have swapped the RiscFree RTL with the updated CV32E40P code and are using the latest Core-5 software tools from the software task group downloaded from Embecosm. The platform is running on the Genesys2 FPGA board, as well as the Digilent Nexus A7 board, and is running with a very simple runtime that can be debugged using OpenOCD and GDB. Source code and instructions to build the platform are available from Open Hardware Group's repo, and this repo is called Core-5 MCU. As well, Ashling have integrated their RISC-free Opella XD JTAG probe with the Pulpissimo RiscFree platform running on the Genesys2. In terms of the next steps for this platform, we're going to proceed with further testing and debugging of the implementation, integration of additional system peripherals, develop a more complex SDK or integrate a more complex SDK into the environment, perform architectural enhancements such as implementing the Open Bus interface, which CV32 now supports, do integration and validation of proprietary and open source tools, both hardware and software, and develop training materials and demos to complete the environment. Just note that we're looking for collaborators in the hardware task group to help with these tasks and also to define new tasks around this environment or other environments. And that's it. Thank you.
Great. Thanks very much. So at this stage, we'll move on to the viewer Q&A, and we'll bring everybody back into the episode and be ready to take your questions that you've entered into the chat room. All right. We have actually quite a few questions that have been typed into the Q&A session. So bear with me while I touch on my screen to read through a bunch of them. I'm going to try to group some of them together. So the way that we typically run the Q&A session is I'll read out the question and then call on the speakers to answer, provide some answers. So there's a few questions related to the platform. So we talked about Digilent quite a bit. They're a partner of the Open Hardware Group, and we have standardized on the Genesys2 and the Nexus FPGA boards. And the Genesys2 FPGA board from Digilent has enough capability in it that we can clearly build MCU class devices, so using the embedded 4-stage core, as well as build the CVA6 application processor with a dual core environment. And the ETH guys actually have done that previously already. And it's a bit more of an expensive board, but we wanted to have one standard board that could accommodate multiple different configurations and allow us to build a Core-5 MCU and then a Core-5 APU. So we had a question around our Core-5 chassis SoC earlier. That's been replaced with the Core-5 APU application processor unit, and that work will start initially as an FPGA-based design, dual-core initially based design, as we get to the CVA6, both in 32-bit and 64-bit mode. We can talk more about that with other, through other questions. The near-term focus is the 32-bit embedded class core, the RISC-V core, and that's the Core-5 MCU, and we're using the Pulpissimo platform as a starting point, as Hugh just mentioned. That's in the Genesys2 platform, as we presented today. It's also in the Nexus platform. And I direct you to an event that we're running together with the Eclipse Foundation and CMC Microsystems that we are going to host on September 15th at the virtual developer event called the Open Source Developer Forum. So go to osdforum.org to register. And through generous support from our sponsorship, we can sell you a heavily discounted Nexus platform. And we'll have hands-on sessions with the IDE that we presented today, the tool chain that we presented today, a bring-up environment for that Nexus platform, integrating the Core-5 MCU. So go check that out and register. It's only $25 to register, and then you get a discount code to buy a Nexus board together with the programming and debug probe for $150 plus shipping. You get your discount code when you register, and you go and buy the board from the Digital site with that discount code. All right, so that actually got a bunch of questions all together. Oh, and there was another question around the 32-bit core, and are we going to tape any of these things out? The Core-5 MCU that we build in the FPGA will also then be built in as an SoC in 22FDX. Global Foundries is a member of the Open Hardware Group, and we'll be building a Core-5 MCU and hard silicon in 22FDX. And the team at CMC will be doing the physical design and layout of that core. And that project is just starting to get defined based on what we put into the FPGA version. And then we'll be taping that out and building somewhere between 1,000 and 10,000 eval kits that we'll make available into the ecosystem. So it's an exciting program, and all of the tool chain support that we've been talking about today will be targeted at that device. Let's see, I covered a lot of questions there, and I haven't let any of the panelists chime in on anything. I don't know, anybody want to add anything around the development environment, the tool chain, the migration as we make it from FPGA to a hardened silicon Core-5 MCU? I see everybody's staring sort of blankly. Yes, go ahead, Jeremy.
I just want to pick up, I did see there was one question. I may have miscommunicated earlier on. The top of tree upstream GCC does not support Core-5, but the existing Pulp tool chain absolutely does. Okay, there seemed to be an impression I said there wasn't a tool chain. So if you compile with GCC or you write assembly code and assemble it, it will work just fine. So just to clarify that point, what we're trying to do is make sure that Core-5 is supported with a fully tested tool chain, not a research tool chain, in top of tree GCC tool chain. Yes,
no, thank you for that. And actually on that thread, there was a question around code quality, and I'm not sure, we'll talk about both. Not sure if the question was code quality of the tool chain code or code quality of the RTL for the actual designs. We'll start maybe with the code quality from a tool chain, and I think Craig even mentioned sort of test coverage or lack thereof. Maybe Jeremy and Craig, you can talk about the GCC tool chain starting point that we have and the suitability for that actually being upstreamed into the main repos.
So it is a research tool chain. I think I'll let Craig actually just briefly, since I've spoken already, say a little bit about what we need to do and the state of that code at the moment.
Yeah, so the quality varies across the code, and one of the major issues that is that the changes aren't particularly documented very well, and there are some formatting issues to fix as well, which are minor. But a lot of this code is written because we want to add features to Pulp. But when you add features for your own platform, you also have to not break any of the other platforms. And I'm not convinced that that's tested very well at the moment. So we may find there are some things to rewrite there. And also, because we're jumping forward 3 years, even if the code is written perfectly, there are still going to be changes that we're going to have to adapt to in GCC. So to answer the question, we can't just take the code as it is. We will have to make changes to it, but it is a good starting point.
Yeah, I think I'll comment on the RTL. I think part of what the industry is recognized that, and the catalyst for bringing the Open Hardware Group together as an ecosystem is the work that has been done in the Pulp platform team at ETH Zurich is very good work. Yes, it is a research environment, clearly. So you got to go into it knowing that. But the whole reason that the Open Hardware Group exists as an ecosystem is to take that as a starting point and turn it into industry quality development and supported by industry resources through this ecosystem. So that's, if you missed episode 1 of Open Hardware TV, we did it, provide an overview on the verification environment, System Verilog UVM verification environment for how we're verifying the cores and updating those. And I think, as I said earlier, the catalyst for bringing all of the industry supporters together was, in fact, the good work starting point that came out of Luca's team at ETH Zurich. Want to talk about, there's a few questions in here about accelerators and adding accelerators to the, adding accelerators to the cores. How do you do that, either to the 32-bit embedded class core or the CVA6 Ariane core? And I'll let, we want to answer that question, I think, from 2 standpoints. One, from physically, how do you do that in the design at a high level? And maybe Florian, you can take that on in terms of how accelerators are attached to the cores. And then we talked about it a little bit in the tool chain and maybe even in the IDE. So I'll flip it back over to the Embecosm team and maybe the Ashling team to talk about that a bit. But first, from a hardware standpoint, Florian, if you can talk to how to add accelerators into these designs.
Yeah, so absolutely. So for both cores, we currently do not provide like an out-of-box solution for very tightly coupled accelerators. So accelerators which sit within the core pipeline. Obviously, the code is a standard Verilog, and you can go in there. But we hope that we can settle on a standardized interface eventually for attaching hardware accelerators for both cores. And then, of course, there's the less tightly coupled accelerators, which sit within the memory hierarchy and are programmable via like the load store unit. And those actually, for the Pulpissimo framework, they have a specialized place on the tightly coupled data memory where this could go, and there are a couple of examples there as well. So depending on what kind of accelerator you're looking, there might be more support right now, and hopefully more support for this tightly coupled in-pipeline accelerators coming later.
So if I pick up on the software side, so
yeah, please do.
If you add an extension using the facilities of Florian, and as Florian said, it is an aspiration to make it very general to add your own custom extensions on top of Core5, then you will need the tool chain. Now, some of the technologies we're starting to push are things like CGen, where the assembler, the disassembler, the simulator are generated automatically from an architecture description. So that hopefully will make it very easy to add extension support within the toolchain. That's not there yet, and it won't be there for a while, but that's the route we're going. When it comes to the compiler, well, that's when you need companies like my company, Embecosm, bit of a sales pitch there, to say, can you actually get the compiler not just to accept these in the assembler, but to automatically generate from C code to pick up your extension. And that is compiler work. And of course, once we've done that, we've got the debugger going, then it's Royshin and her team and the expertise on the IDEs to make sure that your extension can be picked up in the IDE. Royshin?
Yeah, thanks, Jeremy. Absolutely. So, I mean, obviously it possibly depends on the kind of extension, but some of them are relatively straightforward. And then, sometimes people can have, a whole array of additional instructions and so on. So the debugger needs to be able to understand those additional instructions. And in order to do that, we have to, like we have to do some customization work for people who have a custom requirement. And this is a service that we provide, and we already have a framework and a model to manage that. And I guess at that point, then, the debugger will be able to understand those additional instructions. And if there are, I think there can also be changes to the, hardware changes as well, and this can also be handled.
Great, thanks. So sort of related to that, there's been a few questions that have come in around trace and debug in general, and part of what we're working on in the development of the MCU and the APU is a standardized open trace encoder and debug unit that will go into these SoCs, both in FPGA form and then in the hardened SoCs within the Open Hardware group, and have that supported in the Core5 IDE environment that we pull together. Now, obviously, that's for standard extensions that these and the pulp extensions that these devices support. Any custom extensions that you would add or custom instructions that you would add for your own accelerator falls into the category of the way Florian and Jeremy and Roshan just answered that question. But if you're interested in some of that trace work and debug work, that's new work that's going to get started with the Core-V MCU project that we kick off here. That's going to be targeted at 22 FPX. Starting point that we have right now in the Core-V MCU work that Hugh described is for the FPGA platform. And Hugh, maybe you can talk about the work that's been started both with the Genesys2 platform and the Nexus platform as a lead into what we'll have at OSD Forum around the Nexus platform and the different FPGAs that are on those boards.
Sure. So yeah, I mean, I guess I described it a little bit before, but I mean, the current state of the Core-V MCU platform is, it's the Palpissimo platform from ETH Zurich with the CV32 core instantiated. And it's running on the Genesys2 board as well as the Nexus A7, or at least that's where the two boards that we've been currently working on. Palpissimo has been implemented on other Xilinx boards as well, some of the higher end Zinc UltraScale boards and the Vertex boards. But we're focusing, I guess, on the smaller boards, the lower cost boards that are still sufficient for our purposes. What we'll be demonstrating at OSD Forum will be the platform running on the Nexus A7, and as Rick said, there's we have a deal with Digilant to provide these at a reduced cost through the sponsorships for the event as well, and we'll be basically walking through the development environment, how to get it up and running on the board, and how to do some run some code on the board. Right,
so that'll have the Core-V MCU, and I know some of this is repetitive, but these are the questions that are coming in on the Q&A panel. But that'll have the Core-V MCU, which is the updated CV32 core, replacing the original RISC-V core in the Palpissimo platform, as well as a few other changes. And that that's available now on the Open Hardware Group GitHub sites. So just OpenHW a group on GitHub, and you'll find all the repos. Or go to openhwgroup.org, and you'll find the link to all the projects, and we'll take you to the repos. The IDE work is starting up, is there. The Core-5 MCU bit streams for programming the Nexus board are there, or certainly the pull requests are there to get approved for that work. And this is all leading up to the OSD forum. So osdforum.org is where you'd want to go to register for that event, which is this 15th of September. We'll, like you said, we'll have hands-on sessions to walk you through the IDE, walk you through using the tool chain, get code running, get your bitstream loaded, and get code running. Even though it's a virtual event, we can't all be physically together. We're going to try to run this as though we're all in a room in a lab together, executing these tools and on these boards. Let's see. A few things around the 32-bit and 64-bit versions of Ariane. And a full application processor that's in 32-bit mode, and how we're going to get upstream support, like RV64GC, kind of support, but it's RV32GC. So this is a new contribution from Thales that is being reviewed, and Jeremy or Florian, I don't know if either of you guys can speak to what kind of, the intent is full Linux to run on that, but what kind of progress there may be, or your knowledge of that project within Thales that's being contributed. If you have any comments to make, can you make them? And if you don't, that's okay too.
Yeah, absolutely. I can comment a bit on that. So as you said, the pull request is under review, and so we want to tackle this in kind of 2-3 steps. So we have decided on the count yet, but at least step 1 is to get 32-bit GC support in Ariane. This mainly means that the core can also be, so not emulating 32-bit execution, but really having a stripped down version of Ariane for the more kind of embedded and size constrained use cases. And so this was going to be the first pull request is going to tackle that. And then in a second / third pull request, we want to bring the virtual memory and the MMU situation up to 32-bit compatibility. And then, yeah, the goal is definitely to put Linux on both 32 and 64-bit version. And on an SoC level, that should not be too tricky. So I'm pretty confident we can have a single SoC where we can instantiate both 32 and 64-bit Ariane cores.
And from a software perspective, I mean, it's a Zbigniew Chamsky. Underneath that, you've got to have a tool chain, and one of the key things will be getting glibc up and running so that Linux can pick that up. And Zbignew's leading that effort, starting with the tool chain.
Right, good. Another question, a bunch of questions about the IDE environment and running that on a virtual platform, and what interfaces are exposed, and how do you get to all of the resources in the device. Can Rajesh or Roshan, can you talk about what what it would look like to run the Core-5 IDE on a virtual platform and into the SoC, and what the API interface is to access internal registers and pins and state? You guys probably see the question.
I'll probably refer to Rajesh, but I mean, basically, this is, the Open Hardware IDE, or the Core-5 IDE, should I say, can either be connected to a hardware board through a JTAG probe, for example, or it can be used together with a virtual platform. And from a user's point of view, from an interface point of view, it's very similar. You mentioned, like, from point of view of looking at registers and so on. Maybe I'll just hand over to Rajesh. You can get into a little bit more technical detail there.
Yeah, I'll try my best. So here, yeah, there are a couple of questions here. So one was this QEMU integration. The question was like, you have QEMU integration, and then what about other ISS? So the point is that what we support is the TCP IP protocol. And then like, if we have this TCP IP protocol for this ISS and the standard GDP commands are supported, we can have integration with the other third-party ISS as well. And coming to this virtual platform and the real hardware, talking about the APIs, yes, there are lower layer APIs which will be available in Core5 MCU as well, like to access the JTAG, like the very lower, like scan IR or scan DR. You can have the direct command interface, so you can have your own implementation of how to read a particular register, a peripheral register, how to access the value of a pin. So that is also possible using this lower layer APIs. And if you have a good understanding of how the JTAG works, that should be possible. So these were the two questions, one on this virtual platform and one on this QEMU side. I think I did not miss anything. Rick,
yeah,
can you just confirm?
Okay.
Yeah.
Okay, that sounds good. Thank you. Okay, we're at the top of the hour. I want to be respectful of everyone's time. Thanks very much for joining. There was one other question that I just want to answer in closing, and that's there was a question around licensing and how do you get this stuff. This is all open source. The hardware is licensed under SolderPad, which is a wrapper on top of Apache. And then depending on where the software came from and how it was contributed, it's either under Apache as well, or the Eclipse public license, which clearly all the IDE stuff that we're doing is related to that. So it's the end of the hour. Thanks very much for everyone for attending. I want to thank all the speakers for their time in preparing the episode. And please reach out to us either on the GitHub repo, on our site. There's a contact email there that you can ask questions. And if you would like to participate in the ecosystem, we'd love to have you. We continue to grow, and it's an exciting time for open source hardware implementation and all of the software to support it. So thanks everyone for attending episode 3. Bye for now.